Welcome back. Hopefully, everyone got a nice break in the sunny and warm San Diego weather that we've graced you all with. Cure their drought when you invite people to visit. All right, so it is no longer up, but up
Yeah.
next we have Dr. Mary Lowe from Loyola University, Maryland. I'm looking forward to this because I do not actually understand Grover's algorithm at all. Don't tell my funders. So hopefully this will go through. I'm going to. Okay, so we're good. We're live now. Yeah, take it away.
Okay. All right. Well, I'm going to talk about Grover's algorithm and how we teach with it, but I thought that first you have to understand where I'm coming from. Okay, so what happened was at Loyola, we offered our first quantum computing course back in 2023. And then it was three of us worked together. It was me, I'm in physics, and then David Ho in electrical engineering, and Dave Binkley in computer science. And we had to do it together in order to get large enough enrollment so that the administration would allow us to run courses like this. So it was offered first in 2023, then David did it again in 2024, and then he offered Quantum Computing 2 in 2025. And we got good enrollments by cross-listing these courses. Our undergrads are composed of physics, electrical engineering, CS, and data science students, and they are primarily from the sophomore to senior years, but freshmen could enter this course if they had a little more preparation. The prereqs were Calc 1 and intro programming. Quantum computing doesn't require Calc 1, but it does require a certain level of mathematical maturity. So all of our classes are in person and they last 75 minutes. In terms of the readings, we used Tom Wong's book and also these very detailed lecture notes and interactive handouts prepared by David. So in that first quantum computing course, that's like the introduction to it. And we need to prepare these students so that they can ultimately read to other books and the literature. So we use Ket analysis, matrix analysis, quantum circuit diagrams, and we freely move back and forth among all of those things, and all of the notations consistent, which is a big issue if you do want to run your own quantum computing course and want to think about using Qiskit and doing Ket analysis. The whole notation issue is an issue. We also use complex numbers, and we taught it along the way. Then how to handle computers in the course is an issue also. And back in 2023 and 2024, the students did Python exercises at the level of what I'll show today. And in 2023, because we had advanced CS students in the class, they actually wrote a quantum computing simulator, a simple simulator using object-oriented programming, and that effort was led by David Binkley. I would say our engineering and computer science departments are ABET accredited, and if you want this course to count towards majors, you have to have enough in there so that it can count. The effort with the simulator was partially successful. It was essentially written by the CS students and not by everyone else. And so in 2024, David decided to cover Qiskit at an introductory level and didn't do the simulator. When I talk about Grover, this subject is occurring at the end of the course, so the students have had all of that introductory material and the Python programming and all that. But I'm throwing it at you now. And then in 2025, when we ran the Quantum Computing 2 course, we covered quantum Fourier transforms, quantum phase estimation, quantum machine learning, and a few other things. Okay, so the way this is going to work, oh yeah, question?
Sorry, I just have a question. So you said you require calc for this course, but it sounds like you're not actually using.
Correct. We don't use it, but the thing is, this course does require a certain mathematical facility. We don't require linear algebra, so we have to teach that along the way. And we have to teach complex numbers. If you don't require calc, which is the kind of student I have in my introductory general physics class, you can get students with only pre-calc. And you're going to throw them, if you're going to throw them into a quantum computing course, it's not clear they can survive. So after we ran it the first time, I was very glad we made Calc 1 a prereq. I was glad of that. Okay.
Worry about introducing unnecessary barriers, but it sounds like you've thought this through and
That right. We wanted. That's why we didn't want the unnecessary barrier of linear algebra as a prereq. So we didn't require that, and we found that was fine. And complex numbers for our students, it's fine. Those were not the hurdles. We had other hurdles. Okay, so the way this time will go is that I'm going to give you the fast version of Grover's algorithm from a kind of a high-level point of view, and then we'll have two activities. The first activity was run in class, and everybody can get something out of it, no matter what their mathematical proficiency is. And then the second activity shows you how we use Python in the class for teaching quantum computing. Okay, so first of all, the Grover problem deals with the unstructured search. And here's a table that we actually showed in class. And in the name column, you see Star Wars characters whose names are arranged in alphabetical order. And then on the right column, you see what planet they come from, and that's not in any particular order. So the unstructured search problem asks this question. Suppose you want to find out who comes from the planet Mustafar. So if you were to write a classical computer program, you'd probably start at the top of the list, and you'd ask the question, is Camino equal to Mustafar? No. Then your second query would be, is Kashik equal to Mustafar? No. And what happens is Mustafar could occur at the beginning of the list, in the middle, or at the end. On average, you would have to make about n over 2 queries, where n is the length of the list. So if you had 1 million entries in your database, it means that you'd have to ask, on average, 500,000 queries to figure out Mustafar in the list. Okay, what Grover did was he found a way using quantum computing so that the number of queries goes as root n. So if you had 1 million entries in a database, you only make 1,000 queries. There are other examples you can use to try to show how this thing could be useful. In Grover's original paper, he cited a phone book where he said, suppose the names are not alphabetized. Honestly, I don't know if students know what a phone book is anymore. So what we did in the homework and in the activity was that I simplified the table so that we're looking at cities. And so you see 4 different cities. And what you want to do is assign a number to each city. So that's what the index is called. And the idea is, suppose you want to find Oakland, and you want to know what are the restaurants and hotels in Oakland. So you look in your list, find Oakland, and then you look at the index associated with Oakland, which is a 2. Then you go to some other table and look at the 2, and you'll find all the restaurants and hotels in Oakland. So this is a very practical problem, and I think in the course, Grover might be the first time that the students actually see something remotely useful about quantum computing. We also cover the quantum adder, but other books don't have that as one of those beginning algorithms. It was also pointed out to me that classically there are very efficient ways of doing unstructured searches using hash tables. We are not comparing with that. So Grover doesn't compete with that, and I'm not going to talk about that. I thought you might want to see what Grover looked like, and very interestingly, his original training was in electrical engineering. In perspective, what happened was in 1985, Deutsch came out with his first simpler algorithm, and in 94, Shor came out with his algorithm for factoring numbers. 96, Grover came out with his algorithm, and what happens is I think these 3 showed people that quantum computing could be really important. And then you had hardware development in 98, and then in 2016, IBM made the first quantum computer available on the cloud, and then you have a whole series of hardware improvements. So the largest number of qubits is this Microsoft Majorana. I don't know how to pronounce it. Majorana. Majorana? Is it what? They have 0 qubits?
Yeah.
Oh, okay, well, I don't know what's a topological qubit, but anyway, I read 10 to the 6, whatever. Okay. All right, so now let me go into a high-level view of Grover. So now the circuit diagram is shown schematically like this. There are 3 major parts to it. So the first part over here prepares the state to be sent into the Grover operator. The Grover operator has 2 parts. One is called the oracle, and the other one is called the diffusion operator, which is responsible for amplitude amplification. And then what's happening is that you don't know the result of what's going on in the quantum computer until you measure it. So the last part is the measurement. And what we have to do is try to understand what each section is doing. Okay, so let's first go through the preparation of the initial state. So remember, every single city has an index associated with it. So what you do is you start out initializing your qubits to 0. So this is the state right here, psi 0. And then your psi 0 ket starts out as 0, 0, 0 if you are dealing with 8 cities. Okay, now what happens is you apply a Hadamard gate to each one of your qubits. The students do this exercise as soon as they hit multi-qubits. So this is done weeks and weeks ago. So they all know about this. But after you apply the Hadamard gate, what happens is you're going to get a superposition of all of the computational basis states. We can write it in different ways. So for example, we can write it in decimal numbers. So you can have 0 ket plus 1 ket plus 2 ket all the way up to 7 ket if you're dealing with 8 cities. Alternatively, we can write it in binary. Alternatively, if you want to work with computers, you will have to work with matrices and column vectors. You can write it as a column vector like this. And then because this column vector takes up a lot of space on your paper and on the computer screen, you can write it as a row vector, but you have to take the Hermitian transpose or dagger. So you take the dagger so you take this, dagger it, and then you produce this. But for Grover, all the numbers are real, so this thing, the dagger is basically the transpose. And then you have to make sure you normalize everything. So here are your 8 cities, and the question we're going to pose and what you'll work on in your activity is, what is the index of Oakland? So you have to do this search and figure out that the index of Oakland is a 5. Okay, so now the other issue is if you created the superposition state and you try to make a measurement at this stage, what happens is each one of these states has an equal probability, and you haven't singled out any particular state at all. And you want to see the 5 when you make the measurement, and you haven't accomplished that goal yet. Okay, so now you have to send your state into the Grover operator. So first you have to work with the oracle. And in the oracle, what happens is, that's the O operator. When the O acts on the superposition state, what it does is it marks the target state. The target state is a 5. Okay, so we can start counting from 0. So 0, 1, 2, 3, 4, 5. The 5 has a negative sign placed in front of it. And then what we can do is also write it in ket form like this, and the 5 has a negative sign put in front of it. And in the books, they'll talk about how the oracle creates a phase shift for the target ket. Okay, now it's a little bit unsatisfying, but the oracle knows the answer, so that's another issue, but let's just use that. What would the matrix for the oracle look like? Well, it's basically the identity matrix, except that in that 5 position, you have to have a -1 over there. Okay. There's another popular way of representing the results of the oracle of all of the stages in Grover, and that is if you can draw a bar graph where on the horizontal axis you label all of your computational basis states. So you have it going from 0 to 0, 0 up to 1, 1, 1. And then the amplitude of each one of them is the same until you hit the 5 ket. And the 5 ket has an amplitude that's phase shifted, so it's plotted down here. Okay, so we'll be making more of these plots. Now the issue is if you stopped here and made a measurement, what's going to happen is each one of these kets has the same amplitude and consequently the same probability for being measured. And you haven't singled out the target ket at all. So this isn't good enough. So what Grover did was he figured out a way to convert that phase shift into a magnitude change. And so he used the diffusion operator up here for that purpose. Okay, so what he did, there are many levels of understanding, but just from the high level, what this D does is it converts that phase shift into a magnitude difference. So over here, your superposition state has equal amplitude for everything, and then after the oracle, you have phase shifted the target ket, and then after the diffusion operator, you have now made the amplitude of the target ket bigger than that of the others. Okay, now to head towards the activity and also a more quantitative understanding of what's happening and to calculate the number of iterations you need to do Grover, it's helpful to develop a geometric model. And I would say this idea is present in all of the books that I looked at. However, it is much easier if somebody could walk you through it. So that's what I'm doing here. Okay, so what you're going to do is you take the superposition state and you divide it into two parts. So one is the target ket. So in our example, the target ket is a 5. Then you have all of the other states, and you form and the superposition would be 0 ket plus 1 plus 2, 3, 4, 6, and 7. So we call that the non-target kets. We lump that all into a thing called psi non. So what you do is, if you look at the superposition state, you now have a superposition of psi non and the target. And then you have to make sure everything is normalized properly. So the psi non has a normalization factor. More generally, it looks like that, where large n is the number of cities or number of elements. And then you also have to make sure that your superposition state is normalized properly. And so you get this and this. And the other thing to notice is that psi non is orthogonal to the target ket. So what's happening is psi non is a unit vector, effectively, and 5 is a unit vector, effectively. Those two are orthogonal, so these two vectors form an orthonormal pair of basis vectors. And once you do that, you can now plot it on Cartesian plane, and this becomes a problem that we introduced in week 1 of the intro physics course. So you put your psi non unit vector on this horizontal axis, and then you put your target unit vector on the vertical axis. And then any other state has to, since they're all normalized, has to fall somewhere on this circle, but you do have to figure out what angle they correspond to. Now, all of our students are able to do this. Again, we covered this in week 1 of our intro physics. Okay, so the way we introduce the angle is like this. So here's the superposition state. And then instead of writing that square root thing, you convert this into cosine phi. And you convert that into sine phi. And of course, this is normalized. And so using the numbers in the example, cosine phi is root 7 over 8, and sine phi is 1 over root 8. And then you can figure out the angle, which is 20.7 degrees. So now you take your superposition state and plot it on your unit circle, and it's going to be at an angle of 20.7 degrees. So that's your superposition state. Now I'm going to go through what the oracle and diffusion operator do, and then you'll do the activity to see why we need to have iterations. What the oracle does is it flips the sign of the vertical component. So in other words, you take your superposition state, the component in the vertical direction is this. You flip it so that your vector now is this one over here. Okay, so it's a reflection about the horizontal axis. Then what you have to do is apply the diffusion operator. And the diffusion operator does this. Okay, it can be shown that the diffusion operator represents a reflection of this over the superposition vector over here. Okay, so you do a reflection of this blue arrow over this purple arrow to get the red arrow. Okay, so you have now gone through one iteration of the Grover algorithm. Your goal is that you want this final arrow to be as close to the target, which is the vertical axis, as possible. So then what you want to do is another iteration, and hopefully it'll get closer. Okay, and then you can try again. At some point you're going to go farther, and you'll try this on a piece of paper. So this is all pretty fast, but I think if you do the activity, you will see, you will grasp the material better. It'll solidify better. So that's what I'm going to do next, which is the activity. Okay, so on your table, everybody can have a piece of polar paper that looks like this. And then you need a ruler, and you need writing utensils, so you can use colors or you can use your pencil or whatever makes it easier. Okay, and so what you're going to do initially is draw your Cartesian axes. So your use a ruler, and in my case, I made the outer circle at a length of 1. And then you want to draw your initial superposition vector that actually goes into the Grover operator. And I'm going to tell you it's 20.7 degrees. This is for 8 cities. Okay, so first you draw that. Okay. If you finish that, apply the oracle operator, and you'll get a vector that goes down here. It's below the axis by 20.7. And then if you finish that, apply the diffusion operator, and that's a reflection about psi 1. Okay, so you might not remember, psi 1 represents the superposition vector. So do all that, and then try the second iteration and see what happens. And then try the third iteration and see what happens. And the reason I'm making you go more iterations than necessary is so that you can begin to understand how we can compute the number of iterations needed to actually find the target city. If you had a chance to do 2 iterations, you should have seen an improvement in the results. It means that your vector, it gets closer to the vertical axis, which is your target. But if you did 3 iterations, which is shown in this picture, you would see that the situation is getting worse. So you see, so Grover operator is iterated. So O followed by D, then you repeat it, and you have to at some point stop your iterations. So if you do 3 iterations for this problem, you would see that you've made the situation worse. So you've gone too far. You can try to experiment with that. Too far means your vector, in this case the green vector, is now has a smaller vertical component. The vertical component is a measure of how much of the target is, it's like the vertical component is the component of the target ket, or target unit vector. And you're now getting worse because your target's getting smaller. And that vertical component squared would be your probability of measuring it. And you've made your situation worse. Is this point kind of clear? So, yeah.
So when you're doing this on a computer, how do you know you've gone too far unless you measure? Or are you measuring along the way?
Yeah, so my personal belief is this. If you paid attention to your angles, there is a way you can calculate the number of iterations, the optimal number of iterations. So what I think you have to do, I haven't figured out how a real quantum computer does a loop. So what I think you have to do is you have to know initially the number of iterations. Let's say I knew it was 2. Then you build up your hardware, so you go through Grover 2 times, like this. So OD, OD. So you build up your hardware, and then you send your wave function through it, and then make your measurement. That's what I think you have to do, because I can't figure out how you make a Python, how do you make a loop in a quantum computer? Maybe there's a way.
Yes, you have to unfold it like this, so you cannot really make it like this, but you have to figure out the number of iterations, and then you have to design a circuit.
Yeah, that's what I think you have to do. Because you don't have memory. Or I don't know how they would handle memory. Yeah, you used the oracle twice, yeah. Okay, maybe you got the general idea of it. You want to know how to calculate the number of iterations. And this is a remarkable thing. We're going to get exactly the right results using this method. So to calculate the number of iterations, the way you would do it is, this is the superposition state right there. We converted the coefficients into a cosine phi and a sine phi. But suppose you had a lot of qubits. And if you have a lot, then sine phi equals 1 over root n. But suppose you have a lot of qubits, then you can use the small angle approximation. So then phi is roughly equal to 1 over root n. Okay? All right, now, if you could pay attention to how much your vectors are rotating, what you would find is that after the first O followed by the D, this advances by 3 phi from the x-axis. And then when you apply O and D again, this thing rotates by 5 phi. And if you keep on going, you would find that the angle increases by odd multiples of phi. Okay, so to write it more compactly, as you iterate the O and the D, okay, say k times, your angle increases by odd numbers like this and like this. And then what you are going to say is your desired angle is pi over 2. So you're going to assign 2k plus 1 phi to be pi over 2. And then the phi for a large number of qubits is 1 over root n, like that. So then you get this. And then k is a large number, n is a large number. K becomes this. And then you get k equal to that, which is exactly the right result. And then we say that the number of iterations increases as root n. Okay, so in other words, if you know the length of your list, you can then figure out the optimal number of iterations, and then you can then build your circuit that way, so you know how many times you have to iterate, and then you can ultimately measure your result.
In this problem, we always have 2 qubits, I guess, right?
We use 3 qubits for 8 cities, but you can obviously increase the n number of qubits, which you can do in Python.
So I'm confused what each of these x's represents.
Okay, so we were able to divide the superposition state into the target ket, which is the vertical axis. It's a unit vector vertically, and everything else, which we lump together as along the horizontal axis. And there are 2 orthogonal vectors.
Okay, and each of those are represented by 3 qubits.
Yes, this example you worked on is a 3-qubit problem. Yes. Yes.
I have 2 questions. I lost in the story, so I understand how the number of iterations depends only on the length of the list, but the target ket, in the example we were using the 5th one, but I got lost on like how do we know we're looking for this city, not that city, and then it also seems like the length of the list maybe needed to be a power of 2.
Well, it would be, but yes, because if you convert it into qubit form, it would be a power of 2. Yeah, so we need 3 qubits. So we're dealing with the length of a city. That's length of cities as being a power of 2.
But so it was a coincidence that you actually used 8 cities. So I would take I could take 13 cities and then just use 4 qubits.
4 qubits, you want 16 cities, right?
13 cities. What if I have?
Well, then maybe they're blank, so you just don't, so you don't have a city assigned to all indices.
I see. So the length of the list needs to be a power of 2.
Well, as constructed here, yes, but maybe you have blanks for the actual city names. Yeah, Oliver?
So I like you, I'm trying to figure out whether I need to teach this in my class or not, because I've been advised that the Grover and the Shores are too complicated, and that some books include it, some books don't, and it happens that Tom Baum's book does have this,
Mm-hmm.
and I read it, but it was like, I read it when I was tired, and I left it for later, and I realized that there is something to do with the period.
Mm-hmm. This thing is done in other books, yeah.
But these are beautiful slides. I'd love to have them, but I'm also lost. So if you don't mind going to the previous slide. So I get that part. So what Grover does is it does the search.
Oh, sorry.
Okay, and search by index. And you said we asked Oracle, and Oracle magically knows that we're looking for a city with index number 5. If you go back to the one you were on.
This one?
That one, yeah. And so that's what we're doing, and then the result is the speed up is square root of n as opposed to n, which would be in a classical one if you don't use hash maps. But then when you get to here, and then you said how the oracle will tell you the city you're looking for will have the opposite phase of all the other cities. And then you showed the circuits, and then I got lost, and then you had us draw these, and I couldn't draw it because I don't know what O and D do.
So at the moment, all I did was tell you, you can understand mathematically what it is doing, and geometrically, you know there's a flip about the horizontal axis. For D, you just have to take my word for it at the moment that you have to flip over the superposition state. I didn't prove it. I just said do it. Okay, so if you did that, you can then see that you will gradually approach the vertical axis, which is your target. But you can overshoot it too. So you have to stop your iterations.
I have another question. Could you go back to the diagram?
The diagram,
Final result.
you mean the iteration result?
So the final stop where we stop at is not exactly on perpendicular axis,
Correct.
and that means we're doing some approximate, or we're not finding some exact state.
So,
What does that mean?
so what you will see more clearly using Python is that when you make the measurement of this state, you will get a mixture of results. You're going to get the target for the most part when you make the measurement, but you're going to get the other kets as well, just not so many of them. So then looking at the most abundant result, then you know what the target is.
So you repeat the experiment a few times.
Well, in this case, you repeat the Grover process 2 times. But if you had more kets, you would have to repeat it more times, calculate it according to this.
No, I'm just saying, when you measure it, how do you know you've gotten the most abundant result? Well, you would have to
You measure,
repeat the whole thing.
make 1,000 measurements or something, and then you'll see the most abundant result.
Yeah, exactly.
That's right.
The assumption is that it's an NP problem, so it's easy to verify if the solution's correct.
Right.
And so you can just repeat it until you can verify, yes, that solution's correct.
Okay, we can move on now, and because I think this shows you something, but you can see more if you can write a computer program. And this will also show you the level of Python program that's accessible by all of our students. We have EE students and physics students. They take that intro Python course, and then they don't use it, and they're all rusty. So in our case, we want them to have their Python reinforced, so we try to have them do some Python in this course. The CS students are fine. They've been doing it. Okay, so to understand the next activity, what we want to do is actually calculate numbers, and then we can calculate the actual amplitudes. And so the way you're going to do it is I'm going to tell you, there's a way to prove it, and I think it's in Tom's book maybe, that the diffusion operator can be written in this way. That psi represents the superposition state. like this. And what you have to do is see that there's a bra, and there's a ket. And you have to be very clear what's a row vector and what's a column vector. So in your code, you have to be very clear also. And what we want to do is have the code match what we're teaching on using paper and pencil. So what you're going to do is, you know the superposition state. You know what the column vector looks like. So you know what the ket looks like. And then you can figure out what the bra looks like because that's the transpose. And then that I is an identity matrix. So there is a proof for all of this, but just take this as a given right now. And the idea is, I'll walk you through the 2-qubit case, which was the example code that I asked that you download. Suppose you had 4 cities, and you want to find Oakland and the index of Oakland, which is a 2. Okay, so it looks like this. And now what you're going to do is in that code, and you can use these as example commands. We're using the NumPy library over here. And the number of qubits is 2, so you have a maximum of 4 cities. And what you have to do is create that ket. Okay, so in my case, you can do it different ways. In my case, I created the bra. The bra is a row vector, and it's equal to 1, 1, 1, 1 with a normalization constant. So coef is the normalization constant. Now, we make a clear distinction between row vectors and column vectors. And so in using NumPy arrays, the way you do that is these outer square brackets tell you matrix. And then the inner square brackets tell you this is the first element of, in a sense, the first element of the list. And that's the content of the row. So your row consists of 1, 1, 1, 1. But you have to get your bracketing right. Then if you want to create the ket, you do the transpose of the bra. Okay, and then you want to print it out, and if you print it out, you will see clearly, I didn't print, I have to switch to a Jupyter notebook to see the printout, but you will see that one's a row vector and one's a column vector. So we made a decision to handle our NumPy arrays this way. Okay, now what you have to do is create the oracle operator, which is basically an identity matrix except for one spot. So using this command, you create the identity matrix, and then you change one spot of it at that target location to a -1. And then you can print it out. You also have to create the diffusion operator. So remember that formula, 2 psi ket psi bra minus I. Okay, 2 psi ket, and then that at is a way of doing matrix multiplication in Python. There are other commands, but I use that. So this is psi ket psi bra, and then you have to minus the identity matrix. So that produces your diffusion operator. Then what you have to do is have the wave function pass through the circuit. So over here, you take your original superposition state and then apply the oracle to it as a matrix multiplication problem. And then once you get that, you apply the diffusion operator, and you will get that result, which is the first iteration. And what you're going to, if you print it out, you will now see the amplitudes of the results. And then what you want to do is plot it. Okay, so psi1 will come out like that. You should be able to see that after the oracle, it comes out like that. And then after the diffusion operator, it'll come out like that. But you just on your paper, just draw that. Okay, and then do it again. Okay, so, sorry. For the n equals 2, for the 2-qubit problem, it's actually a very artificial case and not normal. You actually wind up with a result where it's completely landed on the target qubit. This is just an example that's not normal. So what I'd like you to do is 3 qubits. So your activity would be 3 qubits. So here's what you can do. Now you have a list of 8 cities. And let's say, here you go. And let's say Oakland has an index of 5. You're trying to find Oakland. So specify your superposition state. Specify your oracle. your diffusion operator, do Grover once, O followed by D. See what you get by plotting that amplitude graph. Then do it again. See what you get by plotting the amplitude graph. And you should see amplitude amplification as a result. So if you want to, if you have the time, you can generalize your code to handle more qubits. And I think as you get to really large number of qubits, you're going to see what problems you'll encounter with a computer. Or you could work on what are your probabilities of each measurement outcome, or you can work on, it turns out the diffusion operator acts as an inversion about the mean. You can write code to show that, or show examples of that. So do this first, and I'll help you, and do this if you're speedy. Okay, yeah.
Sorry to keep asking the same question.
Sure.
Specifying the oracle matrix,
Yeah.
it seems like I already need to know.
The answer. Correct. And that's what's unsatisfying about it. Okay, I will tell you, other people have noticed this, and let me just show you this. This is my last slide. So other people have noticed how unsatisfying this is. So here's a good paper that appeared in the American Journal of Physics. And what Kane did was he actually designed a quantum database. So you don't know in the beginning what's going to be queried. So he had well, it wasn't cities, but let's say cities. He had his database, and then what you have to do is tell it what city you're interested in, and then it has a way to figure out what oracle effectively to use. It computes it, and he has gates and everything for the oracle, and yeah. So people know this issue with the oracle. Yeah, Brian.
When I do this in my class, one of the things we couple this with is a way of using gates to implement a SAT problem.
A what problem?
A satisfiability problem.
Uh-huh.
And so you can design a satisfiability circuit, right, without knowing the answer. You just define the causes and all that, and then use that as your oracle. And we do this as like a student project where they, given a SAT problem, write the circuit that defines an oracle, and then use Grover to solve it. So there are ways you could do this.
Okay. All right. So as the second activity, which would take you to the end of the workshop. Okay. Can you try it with 3 qubits? I also don't know what's the status of getting Python on your computer. So if you don't have it on your computer, can you sit with somebody who does have it on their computer? And yeah.
So use Google Colab.
Oh, you can use Google Colab. That's easy.
One thing I would say, okay, so I shared the folder with Mary's Jupyter Notebook and all that, which I think is the starting point you want to do from. So if you can get on to that folder through your Google account, you can access that. But if everyone edits that one, we'll all be fighting with each other.
Yeah.
So the first thing I would do is copy and rename it with your name on it, and then you'll have your own version in that folder to edit as you like. But you should also be able to just right-click, open in Google Colab, and then you won't need a local install for Python.
Yeah, that's good. And you can also just retype everything. So if you want, the weird setup that I have here, wait a minute. If it's easier for you, just retype the n equals 2, the 2 qubit case. These are all the commands. Retype that, and then for your n equals 3 case, convert the commands over. So I don't know what your status is with your Python. So, okay, so first of all, let's make sure everyone has something to look at. So does anybody need help with getting Python going? You're either doing it yourself or you're with someone? Okay, so it looks like everyone has their Python going. Okay, the next step would be just to get something running. So can you get the 2 qubit case running? Oh, by the way, our students are like all over the place in the classroom. So you have to find ways to get it all under control. So can you get your 2-qubit case to run? So that would tell me if your libraries are installed and if you've typed your commands correctly.
So I got it running, and
Okay.
I was wondering, but I'm not understanding the output.
Okay, so you want to understand the output.
Yeah.
Okay.
So
Oh, here, or maybe other.
socket, I don't know.
Here,
how
wait, I think I have the output here, then I can go over. Okay, so Oliver, which output don't you understand? That's your psi ket. The psi 1 ket over here?
Why is it 0.5? Shouldn't it be? Yes, it's a cat.
Yes, but you have to normalize. All vectors, all wave functions have a normalization norm of 1.
Okay, yeah, so it's 1 over square root of 2. Okay,
I haven't
instead of.
run it yet.
1 over, no, so if you want to test if this is normalized properly, you square each one. So this becomes 1/4 plus 1/4 plus 1/4 plus 1/4. It has to total 1. Yeah.
So yeah, this is my.
Show the code. Okay.
So now if I have 8, I have to make it as.
But now my coding skills are.
Show the code and somehow type it in. If you have 8, your normalization is 1 over root 8.
To loop. Well, so I just.
Okay. Does somebody need me to help?
2 code to 3.
There are extensions if you want to try them. So they're listed at the bottom if you are finished with your exercise. I already mentioned Kane's approach because he was able to show how to create a quantum database with 2 qubits, and then you don't have to know the answer before you work on Grover. And then you can also see different ways of representing the diffusion operator in terms of gates. So that appears in a number of books. You can also work on a gate representation of the oracle operator. And then I don't know if Grover by itself is extremely useful, but it is incorporated into other types of problems involving searching. So they would include cryptography, optimization, and quantum machine learning. And also this idea of mapping using an angle, that appears in quantum machine learning. And the other things you can do with your students is if you want a more general mathematical understanding of the whole thing, you could go into that. And then if you want to, you can also see how Qiskit and Penny Lane implement it. But we like to teach using simple Python commands only because our students need more practice with Python, and it's very close to the way we teach our quantum computing in our course. So that's it, everyone. Thanks.